The event loop. Now I'm going to share a piece of information which might sound a little shocking. The UI of any application runs on a single thread. Yes, just a single thread. Even in this day and age of multi-core machines with computers, laptops, and even phones that have multiple cores, the UI still runs on a single thread. So let's see why that is the case. Now, if you look at the high-level architecture of any system, you can see these four layers. There is the application layer right at the top that interacts with the user. The windows inside your application are managed by the Windows Server, which of course is managed by the operating system, and the operating system is the one that abstracts all of the hardware from you. Now, if you think out the major responsibilities of the UI, there are two that stand out distinctly. One is to draw things onto the screen, and the other is to accept events from the user. Now, these two operations actually run in opposite directions to each other and go through those same four layers. The drawing operations are issued by the application, which go through the Windows Server, operating system, and finally ending up on the hardware, which is most likely your GPU. On the other hand, the events actually originate at the hardware. It happens when a user presses on a keyboard, clicks on a mouse, or taps on a touchpad. These are all hardware events that propagate up the stack into the application. Now, if we have to realize the dream of multi-threaded UIs, these two operations have to run on separate threads. So drawing and events have to run on a separate thread. Now, but these two threads will be sharing the same four layers in between, and there could be shared state as you tackle some of those actions that need to happen on those different layers. So imagine the situation where you are trying to paint something onto the screen, and at the same time, you want to handle an event as well. Which one should be done first? Should we paint first, or should we handle the event first? Well, there's no clear way to know that because these two threads are not talking to each other. Now, if you want to establish a guarantee on the order of operations, then these two threads do have to talk to each other. And that means they have to have some kind of a synchronization happening between the two. Now, two threads talking to each other and sharing state is like the black art of software engineering. It really requires you to think hard and it complicates the programming model quite a bit. In fact, you will have situations like deadlocks, race conditions, and synchronization complexities that need to happen between the two threads. Now, our industry has actually tried the multi-threaded approach before. With Java AWT back in the 1990s by Sun Microsystems, decided to create a multi-threaded version of the toolkit with the graphics and even handling running on separate threads. For the programmer, this was definitely not fun. It led to a lot of crashes in the UI and the application, and there was always complaints on the forums about sequencing the graphics and event handling operations. The raw graphics performance was also not very great. Eventually, they abandoned this particular approach and went back to a single-threaded UI. It was also the approach taken by Java Swing, the successor to AWT. And it's not just Java Swing. All major leading vendors of UI platforms today use the single-threaded approach to create and run the UI. So single thread is here to stay. But there's one problem with the single-threaded approach. A thread starts executing with the first instruction and goes all the way to the last instruction and then simply quits. That's the end of the thread. But UIs don't work like this. We need to wait for the user to supply us inputs and then taking a specific instruction from the user to close the thread, like clicking on the X button in Windows or the close button or the quit button somewhere, and so on. So we have to wait for the user to tell us when to stop executing. But with a single thread, how do you do that? Moreover, most applications request data with a network call. They could be spawning off a separate process or a thread, running timers, and also accept events from the user. How do you do all that with a single thread? So imagine the situation where your main thread is coming to a point where it executes an instruction to spawn a new thread. Well, the thread is created and that runs off and doing its own thing, whereas the main thread continues its job and finishes to the end. Meanwhile, the spawned off thread also runs to completion and has to notify the main thread that it's done. But guess what? The main thread is dead. There's nobody there to listen to that particular notification. Now we have to do something to make this main thread wait. Just wait for others to notify it. And the only way a single thread can wait is by running some kind of an infinite loop. Literally a while loop that runs forever. Now this is what is normally known as the event loop. The event loop is literally a loop that runs forever and waits on notifications from the outside world. But the heart of the event loop is a simple data structure called the queue, or the message queue. It's a first in, first out data structure that respects the order of the messages and notification that it receives. Messages that come in first get handled first. First come, first served, my friend. Now, the event loop is known by different names on different platforms. Run loop on macOS, message loop or message pump in Windows. Gaming engines call it game loop or main loop. And similarly, the message queue itself also has other names like the task queue. Now, as messages and notifications arrive, they are put into this queue in exactly the same order that they arrive. So, this ensures the order of operations and the sequence. And from our previous example where the spawn thread notifies the main thread, is seen as a message inside this queue. Now, in every iteration of the event loop, a message from the queue will be processed, and then it'll move on to the next one. And this will continue as long as there are messages inside this queue. And when there are no more messages, the loop kind of goes into an idle state. Now, kind of glossed over the concept of processing a message. What really happens is that in every iteration of the loop, it'll block till the message is completely processed. And this really translates to a function being executed on the call stack. And these functions can also execute more functions, and that builds up the call stack until it completes. And at that point, that message is considered being processed, and then the loop continues to move on to the next set of messages. Now, I want to highlight the fact that in every iteration of the loop, it's going to block and wait till the message completes, which means it's actually a synchronous operation. So you have to be careful to ensure that these messages don't actually execute for a very long time and build up a deep and long running call stack. Well, you may have encountered a situation where you click on a button and the UI just takes forever. Well, that's what happens when you run a long running message. The application just hangs on you. It has no way to process ahead because guess what? It's a synchronous loop that's executing over there. Now, the holy grail of a performant event loop is to run at 60 frames per second, which only gives you about 16 milliseconds per frame or per loop iteration. This means you have to execute your callback and messages pretty quickly, within 16 milliseconds. Now, it's interesting to note why we chose the number 60 frames per second. This happens to be the refresh rate of most standard displays today. At the end of each iteration, the UI is going to paint something onto the screen. And having a 60 frames per second refresh rate means that your loop also has to complete that many times per second, giving you only 16 milliseconds per loop iteration. Now, the last thing I want to cover are the event sources that can contribute messages into the queue. There are several actually. I/O being one of them, network requests, timers, system or hardware events such as a sensor input, and even user events coming from your input devices. Now, in some implementations of the event loop, certain event sources like the user events are given higher priority. In fact, the messages for these sources are even moved into their own queue to be processed before the other messages get processed. Giving higher priority to certain event sources like the user events results in a better user experience. And that's what it means to be really user friendly. So, that's in a nutshell what an event loop is all about. It's about making things work on a single thread and giving you that feeling of concurrency where you can do multiple things even though you only have one thread. The real gem of an idea over here is the concept of the event loop and using a message queue and having multiple sources that can pump messages into this queue. But make sure you process your messages in 16 milliseconds because that's what you want to build, a 60 frames per second event loop which will get you that high performance, buttery smooth UI.